Hello friends, welcome back. The last two videos taught us divergence, a local property at every point of a vector field, and curl. Today we move from local to global with the divergence theorem. The statement is simple but powerful. The flux of A through a closed surface S equals the integral of the divergence of A over the volume V enclosed by S. In symbols, the closed surface integral of A dot ds equals the triple volume integral of nabla dot A dv. Why does this work intuitively? Imagine cutting V into millions of tiny boxes. Each box has its own little flux outflow given by its divergence times its volume. When you add them all up, every interior face is shared between two boxes. The flux out of one is flux into its neighbor, so they cancel. The only surfaces that survive the sum are the outermost ones, which is exactly the boundary surface S. So the sum of every tiny divergence equals the total flux through the outer skin. That is the divergence theorem. This is one of the most useful results in electromagnetics. It turns Maxwell's differential law nabla.E equals rho over epsilon 0 into Gauss's law in integral form. The total flux of E through any closed surface equals the enclosed charge divided by epsilon 0. We will see exactly how that happens at the end of the video. Worked example 1, a unit cube. Let A be the same field we have been carrying since PS05, x squared y x hat plus y squared z y hat plus z squared x z hat. Take V to be the unit cube, x, y, z, each between 0 and 1. We will compute both sides of the divergence theorem and check they agree. Volume side first. The divergence we already know. PS05 computed it. Nabla.A equals 2xy plus 2yz plus 2zx. Triple integral over the unit cube. By symmetry, each of the three terms gives the same answer. Integrate 2xy over the cube. The integrals separate. 2 times the integral of x from 0 to 1 times the integral of y from 0 to 1 times the integral of dz from 0 to 1. That is 2 times 1/2 times 1/2 times 1, which is 1/2. 3 identical terms gives 3 halves, so the volume side is 3 over 2. Now the surface side. The cube has 6 faces. We hit each one. On the face x equals 0, the outward normal is minus x hat, and a dot minus x hat equals minus ax equals minus x squared y, which is 0 on the face. So that face gives 0. By the same logic, the faces y equals 0 and z equals 0 each give 0. Only 3 faces are alive. On the face x equals 1, the outward normal is x hat. A dot x hat is x squared y, which is 1 squared times y equal to y. Integrate y over y from 0 to 1 and z from 0 to 1. That is 1/2 times 1 equals 1/2. On the face y equals 1, a dot y hat is y squared z, which is z. Integrate z dx dz equals 1/2. Same for the face z equals 1. 3 faces, each contributes 1/2, total 3 over 2. Both sides match. 3 over 2 equals 3 over 2. The divergence theorem is verified for this cube and this field. Worked example 2. A sphere of radius r with the inverse square radial field from PS05 and PS06. A equals 1 over r squared in r hat. This one is going to be subtle because the field is singular at the origin, and that is exactly where the lesson lives. Volume side first. Inside the sphere, but excluding the origin, the divergence we computed in PS05, nabla.A, is 0. So if you naively integrate 0 over the volume, you get 0. Hold that. Surface side. On the sphere of radius r, A dot r hat equals 1 over r squared. The surface element of a sphere is r squared sine theta d phi. So A dot ds becomes 1 over r squared times times sine theta d phi. The r squareds cancel. We are left with sine theta d theta integrated from 0 to pi and d phi integrated from 0 to 2 pi. Sine theta from 0 to pi gives 2, d phi gives 2 pi, product 4 pi. The surface integral of A dot ds is 4 pi. Stop and feel the contradiction. The volume side gave 0, the surface side gave 4 pi. The divergence theorem says they should match. What went wrong? Nothing went wrong. The issue is that nabla.a is not 0 at the origin, it is infinite. Specifically, nabla.a equals 4 pi times the three-dimensional Dirac delta function at the origin. When you integrate that delta over the volume, you pick out 4 pi, exactly matching the surface side. The divergence theorem is restored, but only because we are honest about the singularity. And here is why this matters. Multiply both sides by q over 4 pi epsilon 0. The field 1 over r squared r hat becomes the electric field of a point charge q. The surface integral becomes the flux of E. The volume side becomes q over epsilon 0, the enclosed charge over epsilon 0. That is Gauss's law in integral form. Gauss's law is exactly the divergence theorem applied to the inverse square field, with the singularity properly handled. Every Gaussian surface calculation in electrostatics is built on this. Quick recap. The divergence theorem says the flux of a vector field through any closed surface equals the volume integral of its divergence inside. Local sources, summed up, equal global flux. Two worked examples. First, the unit cube with the polynomial field from PS05. Both sides came out to 3/2. That is a clean, no tricks verification. Pick a region, pick a field, both sides match. Second, a sphere with the inverse square radial field from PS06. Naive volume integral gave 0, surface integral gave 4 pi. The mismatch was resolved by recognizing that the divergence is a delta function at the origin, not 0. Multiply through by q over 4 pi epsilon 0, and the result is Gauss's law. Flux of E through any closed surface equals enclosed charge over epsilon 0. Every Gauss surface problem we will see, cylindrical shell, charge plane, coaxial cable, rides on this theorem. Instead of integrating flux head-on, we choose a surface matched to the symmetry, make the integral trivial, and tie the result to the enclosed charge. The whole trick is the reward of the divergence theorem. Next time, the partner result, Stokes' theorem, which connects curl to circulation around a closed loop, and Maxwell's other two integral equations come out of it. See you then.